Greetings everyone, I am Bitojit from Indian Statistical Institute. Let me first thank the organizers for arranging this special session and allowing us to present our results on quantum error correction in near-term systems. I will briefly introduce quantum computing and then we'll move to two of our results. A classical bit can be either 0 or 1, but a quantum bit has this property that it can be in a linear superposition of them. So this is called a block sphere. This is the mathematical representation of a quantum bit or a qubit. And this up arrow is 0, down arrow is 1. This is classical, but in quantum, any point on this block sphere is a valid qubit. The underlying physics is something like this, that it is an enharmonic oscillator and these are the energy spectrums. The lowest two energy spectrums are 0 and 1, but as we see that higher energy spectrums exist as well. So this will be 2, this will be 3 and so on. And if we move to higher dimensional systems, the computational space increases and has some beautiful applications in quantum cryptography, quantum random walk algorithms, etc. However, as we move to higher dimensional systems, the circuit cost increases and makes the circuit more prone to errors. So we have already seen the physics and the mathematical representation, but these are the real devices that are present with us today. So this is the 5 qubit quantum chip from IBM, but they already have many more qubits. It is around 60 qubits now what they have. And this is the Google Sycamore chip, which is a 54 qubit chip. However, the properties of all these chips are that the number of qubits is small, it is less than 100. These qubits are noisy. That means you cannot apply a large number of operations on them, because if you do that, the error tends to dominate. And even these operations, called the quantum gates, they are imperfect as well. Therefore, error correction is necessary. However, the action of this error or noise on the qubits are represented by noise models, and there are different type of noise models. I'll talk in more detail about the depolarizing noise model, which we will follow in this entire talk. However, there are other things like amplitude damping and phase damping. What happens in amplitude damping is that if the system is in the state 1, it naturally tries to decay to state 0. And in phase damping, the relative phase between 0 and 1 in a superposition state changes naturally. Now, consider a quantum state here, and the error actually shifts the quantum system from its original configuration. So it is an unwanted operator, and Peter Shaw showed that for any unitary error, you can write it as a linear combination of these Pauli matrices. Identity sigma x, sigma y, sigma z, these are called Pauli matrices, and the sources of errors are usually twofold. One is the gate error, which is introduced by imperfection in the operations, and the other is called the memory error, which is basically imperfections on the qubits themselves. Even if the qubit is lying idle, they can incur error. So we require error correction, but error correction has some penalties. It restricts the speed up because we are spending more time on correcting the errors. And suppose we in general have n many qubits, but when we go for error correction, we are down to fewer number of logical qubits, error corrected qubits. So even after paying this much penalty, this is a result which shows that we cannot nullify the error probability. So this is a 2-qubit QFT circuit, quantum Fourier transform, and we show that if we don't apply any QECC, then for the 2 qubits, these are the error probabilities 7 and 5 of the order of 10 to the power minus 6. But after applying 9 QECC blocks after every gate, we have been able to reduce the error probability from 5 down to 3. So it seems like a huge penalty to give 9 error correcting blocks just to reduce the error probability slightly. It cannot be 0. So this motivates us to our first result, that we want to reduce the number of QECC blocks. How to do that? So we say that the sources of errors are twofold. So first we concentrate on gate errors. Given any technology, for example, IBM is using the superconductors, then we have Xanadu using photonics, and there are ion traps and many others. There are a set of gates which can be directly implemented there, and we call those primitive gates. And take the set of all those primitive gates, and the worst error probability we term as omega. We associate this omega with each and every primitive gate. But those gates which are not primitive, say this CZ gate, control Z gate on nonlinear photonics, it is not primitive, so it needs to be broken down in terms of primitive gates. For those, we find out the error probability in this way. See, there are 2 RZ gates, So the probability of no error is 1 minus probability of Rz taken twice square. Similarly, we take the product of each and every gate, the probability of no error for each and every gate, and we subtract the product from unity. This gives us the probability of a non-primitive gate. So we can find out the probability of any non-primitive gate using this technique. The second is the memory error, and here we show an example. We take the technology quantum dot, and these are the gate times which we obtained from this paper by Suchara. So the idea is we take a timestamp for both Q0 and Q1. It starts with 0, and the first gate, this Hadamard gate, is applied on the qubit Q1. It takes 12 nanoseconds. So the timestamp of Q1 increases to 12, but the timestamp of Q0 is still 0. Now, when we have a 2-qubit gate like this CNOT gate, we will put it on the maximum of the timestamp of the 2 qubits, which is 12 here. Now, it is 27 nanoseconds, so we have the 39 nanoseconds, both the timestamp increases to 39 nanoseconds, and we see that the first qubit has been idle for this time, 12 nanoseconds here. Similarly, we put this X gate on the first qubit, and the timestamp increases to 49, but here we see that it is idle for 10 nanoseconds. So this technique basically uses that we want to place the gates as densely as possible and then find out how many timestamps each of the qubits are remaining idle. And from that, we can easily find out the memory error probability of each qubit, taking the values into consideration. So once we have these two techniques, the user can specify a tolerable error threshold, which we call here PTH. And then the idea is that you trace through the entire circuit, calculate gate errors and memory error probability for each qubit. And whenever you come to a timestamp where the error probability of the circuit is increasing this predefined PTH, threshold error probability, prior to that, you place an error correcting block. So using this technique, we show two results here. There are multiple results in our paper. So for quantum Fourier transform and for reversible adders, we see that this is the number of gates that was originally there. So those many error correcting blocks would have been required, but we have been able to reduce the number of error correcting blocks significantly. So this is a very interesting result that we have with us. Now we move to a second part where we work with ternary quantum systems. Now, as we said that as we move to higher dimensional systems, the circuit cost increases. So for near-term systems, we are not able to give that much of cost. So we want to come to some approximation. So let's see how. So first we come to what is a stabilizer, and the example is using a qubit because it is easier to show. So suppose this is the encoding of a qubit. This is the original information which is encoded into some higher number of qubits. And we have this Pauli operator sigma z, which acts on 0, it gives a +1 eigenvalue, and when it acts on 1, it gives a -1 eigenvalue. The properties of stabilizer is that a stabilizer, which is basically an operator created from all these, it should be a +1 eigenstate. So the original code word should be a +1 eigenstate of the stabilizer. But if there is an error, this eigenvalue should become -1, from which you will be able to identify it. So take this example here. This sigma x means a bit flip error. So the first qubit is actually flipped, and you see that these two stabilizers, this value has become -1. So for different errors, we will have different patterns of -1 from which we can understand which error has occurred. If we move to ternary systems, the stabilizers are created from these operators, and the action is x1 actually increases the state by 1 modulo 3, and x2 by 2 modulo 3, and z1 actually gives the phase of omega on 1 and omega square on 2, and z2 is its complex conjugate. Now, when we build a stabilizer on error state, now the eigenvalues are omega or omega square, but on error-free state, the eigenvalue is still +1. So first we come to phase error correction. This is our encoding scheme. This is x1 and x2 we call bit errors, z1, z2 phase errors, and these take it together, it is called the y error. These are our two stabilizers. So if you see that this stabilizer acts on a subset of qubits, we call it G1, and this stabilizer acts on some other subset of qubit, which we call G2. So these two stabilizers kind of partitions the set of qubits. And if an error occurs on this partition, then this stabilizer will have non-unity eigenvalue. And otherwise, if an error occurs on this partition, then S2 will have a non-unity eigenvalue. So if at any point S1 and S2 both have non-identity eigenvalue, then what we can say is that we have simultaneous phase errors on G1 and G2. Now let's focus on one of the sets G1. G2 will be exactly similar. So we have three qubits Q1, Q2, Q3. If Z1 error occurs on it, these are the stabilizers. So here we see that Q3 and Q5 has the same stabilizer pattern. So we correct for any one of them. It doesn't matter. Now what happens if two qubits simultaneously has phase errors? Here we see for these two, the errors actually nullify each other. So effectively there is no error. But here this pattern is similar to Q1. So we don't know whether Q3, Q5 has occurred or Q1 has occurred. But since the effect is similar, we can correct for Q1. Similarly, we can show it for three simultaneous errors as well. And this we are showing for the set G1. You can equally try it out on set G2. So for each set, three simultaneous phase errors can be corrected. And we already argued previously that since the stabilizer partitions the set, if both the stabilizers are non-unity, that means phase error has occurred on both of them. So simultaneous phase errors on both the sets can be corrected. Simultaneous phase errors on each set can be corrected. So we claim that this QACC can correct up to 6 simultaneous phase errors on the code word. Now coming to bit errors, here we see that the stabilizer shows it can detect each and every bit error, but if the bit error is on Q2 or Q3, the stabilizers are same and it can detect, but it cannot uniquely identify the location of error. So this is what we say it is approximate. It is detecting, but it is not able to identify, so it cannot correct the error. But why is this important? First, we see that we can correct up to 6 phase errors. Yes, we cannot correct a single bit error here, a single scenario of bit error, but we can detect it. And at the same time, given this 9 qubit QACC, we have more than 55% reduction in the gate cost. And that is where this actually outperforms the 9 qubit QACC for near-term systems. And this is the way we calculate the probability. If the probability of the errors, Pauli errors, sigma x, sigma y, and sigma z are same, then we show that on average, the error can be a single error, can be corrected with probability 0.75. But if we have an asymmetric error, which is much more realistic, where the probability of bit error is much lower than the probability of phase error, in such a scenario where here we have taken that the probability of bit error is 100 times lower than that of phase error, then we see that a single error can be corrected with almost certainty. So these are our two results that we wanted to share with you. And if you have any comments or any queries, any suggestions, please feel free to drop an email or in Twitter or in LinkedIn. And thank you very much.